But before I start actually going through the notes I have here, I want to use a different analogy. Let's say you want to go to the store and you want to buy some eggs, and you want to buy 144 eggs. Do you go and buy them individually? No. How do we typically buy eggs? Yeah, you buy in groups of a dozen. And I like to start with this analogy because I think students, you intuitively know, you don't buy one egg at a time typically, right? You buy a dozen or maybe 2.5 dozen. Maybe you buy one of those big 5 dozen things at Costco. But you don't ever buy things one at a time because it's kind of ridiculous. Okay. Well, we actually have a very similar concept in chemistry involving how many particles we have. If we were to count up individual particles and go, there's one particle of water and there's another particle of water. If I were to look even in a little bit of...
Mr. Cleaver, you have a call on line 2. Mr. Cleaver, line 2.
If I were just to look in the little bit of water I have in my water bottle right here, there's probably billions of particles in there. Does that make sense? And why would we count them one at a time? Who's going to go through with a magnifying glass, a really good microscope, and count one particle? 2. Does that make sense? So we have a similar thing here. We don't count particles one at a time. But in the egg business or the donut business, we measure them in dozens. In the chemistry business, the term we use is called a mole. Does that make sense? A mole then has been defined as this ratio right here. And I'd highly recommend you write this down somewhere important. I'll even use the highlighter here. Sometimes it's called Avogadro's number. A mole is 6.02 times 10 to the 23 atoms. And there's a lot of information we need to unpack with just that one thing I highlighted there. Okay, so here's my first question. Have you guys ever worked before in a math class with the number times 10 to the power of 23. Have you guys ever used that sort of notation before? Or is that new? What was that? Never seen it before, or you have?
We've used powers, but not like
really. Okay, so maybe let's just take it from the beginning in case you guys have no idea what this means. Sometimes in chemistry and physics and science, numbers are so big or so incredibly small that writing them out in like a regular number format is not plausible. Let me give you an example. Let's say I wanted you to tell me how far it was from here to the sun. I believe it's 153 million miles. That's a fairly big number. It's going to get a little bit tedious to write all those zeros every single time. Does that make sense? So scientists have developed a shorthand way of shortening up numbers so we don't have to write all those zeros every single time. And it's called exponential notation. Here's how exponential notation works. Rather than include all of these digits, what we do is we take the decimal point and we move the decimal point over a certain number of times. So for example, imagine there was a decimal point right here at the end. I would move it over 1, 2, 3, 4, 5, 6, 7, 8. I'm going to move it over 8 times. Here's how I would write that number now. I would write it as 1.53. And then how many times did I move it over? 8 times. But each time I move a decimal place over, I'm affecting it by 10. You guys know how like this is the ones digit, the tens digit, the hundreds digit? So the way we write it then is times 10 to the 8. And it shortens up the number sometimes. I mean, I know it's not that much shorter, but rather than writing out all of these digits, we move the decimal place over 1, 2, 3, 4, 5, 6, 7, 8 times. And so this is a new way of writing this value. Well, that's what this one here has been written as. 6.02 times 10 to the 23 is a large number of atoms. If you can imagine, I mean, like I said, even just a little bit of water in my water bottle here, there are billions upon billions of atoms in there. And so to try to actually write that number out is so many zeros that we have to shorten it up. I'm actually going to write this number now with all of those zeros. Okay. First I'm going to write 6. Then I'm going to move the decimal place over once. So that would be then an O and then a 2. I've now moved the decimal place over 2 times. Does that make sense? How I moved it once here another time there. But that's only 2 times out of 23. So then I need another 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm running out of room. 17, 18, 19, 20, 21, 22, 23. That is how big that number would be. Do you guys get the reason as to why I would not write that number every single time? It's kind of ridiculous to write that many zeros. Actually, I think I wrote too many zeros. Work backwards. Let's just make sure I did it right. If here is the last number, this is where the decimal place would go. I'm going to move it back now 23 times. 1, 2, 3, 4, 5. That would be over here then. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 times, and then I write it as 6.02. That makes sense. Let me try a few more examples. Maybe just write this on the back of a sheet of paper somewhere, because there's a lot to even just understanding how this sort of number works. Let's say I wrote the number 9,000. If I wanted to write this in scientific notation, granted 9,000 is not that big of a number. Where is the decimal point located? Yeah, like right here. So let's start moving it over. Let's move it over 1 time, 2 times, 3 times. I could say that 9,000 is the same thing as 9 times 10. And then how many times did I move the decimal place? 3. Is 9,000 equal to 9 times 10 to the 3? Yeah, because really it's like 9 times 10 times 10 again times 10 again. That is equal to 9,000. This notation here is known as scientific notation. Or sometimes it's known as exponential notation. Let me do another example, just to make sure this is kind of sinking in. Let's say I gave you the number 185,000,000,000,000,000. A very large number. How can I shorten up and write it in exponential notation? So, start at the back. Where's the decimal place? Right there. How many times can I move it over? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We typically stop with 1 number left to go. Does that make sense? So I didn't go past the 1. We make the 1 stay in front of the decimal place. So now this number gets written as 1.85 times 10. And then how many times did I do that?
11.
Is this a shorter way of writing that number?
Yeah.
Yeah. Right now, I mean, is it always shorter? Well, I got to be honest. 9,000 written as 9 times 10 to the 3, it's about the same. But you can hopefully see how this is useful when you're talking about very large numbers. It's actually also useful when talking about very small numbers. Let me show you a different example. Let's say I ask you to determine the width of an atom, like the size of an atom. Very, very tiny. The size of an atom might be 0.0000000000005 meters across. That makes sense? Like we're talking something so infinitely tiny that I don't even think we can't even measure it. It's so small. Does that make sense? Often in physics, when we're talking about atoms, or in biology, when we're talking about cells, we talk about things so entirely small that there's so many zeros in front of the number. Does that make sense? We can still use scientific notation. It changes a little bit. Where's the decimal place located? Actually, here it's written out. It's right there. Does that make sense? But rather than moving the decimal place that way to the left, This time we're going to move the decimal place this way to the right. Watch with me. I'm going to move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I'm actually going to go one further. I'm going to make it go 12 times. Because that means the decimal place is now just on the other side of my first digit, which is 5. And here's how we write this. It's 5 times 10. You know how I move it 12 times? That implies a very big number. Doing this makes it very small. We use a negative exponent. A negative exponent implies a very small number. So a positive exponent means make the number bigger and bigger and bigger, 10 times over, 11 times. This number right here actually means make the number smaller, over and over and over, 10 times. Does that make sense at all? We're going to use this a little bit over the next little while, especially in physics. It's very, very, like I introduced this in chemistry, and it's going to come up once in a blue moon in chemistry. But really, well, the reason why I want to show you this notation now is because when we do a lot of calculations in physics, a lot of times the numbers are very large. Sometimes they're very small. And if I asked you to write this number out over and over again, it gets a little tedious. Let me try one more example just to make sure you guys get the hang of it. Let's say I told you that something was 3.17 times 10 to the minus 4. What does that mean? Is this a big number or a small number? Okay, so as a small number, and by the way, we know it's small because there's a little negative exponent. It means we have to move the decimal place over 4 times, so we have to move it over in such a way that it makes the number smaller. If I move the decimal place this way, it would make it 31 or 317, and that's making it bigger. So I have to move the decimal place the other way. So let me just undo what I did there. I'm going to move the decimal place over 1 time. Then I'm going to move it over a 2nd time, and I'm going to put a 0 there. A 3rd time, I'm going to put a 0 there. A 4th time, I'm going to put a 0 there. And I'm going to put one more 0 right here to make it 0.000317. And this is the shorter way of writing this number because it's been moved. If you watch with me, it's been moved 1, 2, 3, 4 times. In a way, this 4 right here, see how there's 1, 2, 3, 4 zeros? That's kind of what that 4 kind of does to the number. Does that make sense? If you want more practice on that, let me know, okay? I can make up numbers for you to practice. But this is a really important concept, the idea of how do we work with numbers that are either really big or really small. And in our class, when we talk about how many atoms something has, stuff has a lot of atoms. So we're going to need this notation a lot. Does that work so far? Okay. Bit of a side note then. If 1 mole is a lot of atoms, kind of like how a dozen equals 12, does that make sense? The question might arise, well, why did scientists choose this number? It's kind of a random number. So in case it matters to you, scientists chose this number because this is how many atoms make up 12 grams of carbon-12. That's actually the reason behind why they chose this particular number here. It wasn't just by accident. I want to try an example here. Let's say that you have 4 moles of magnesium chloride. Let me change the example here, actually. Let's say that you went to the store and you bought 4 dozen donuts. How many donuts is 4 dozen donuts? 48. How did you figure out 48, though? Yeah, but what did you do in your brain? 4 times 12. Why did you pick 12, though? Because 12 is a dozen. Okay. Well, we're going to do exactly the same kind of thing, only rather than multiplying by 12, because 12 isn't a dozen, I'm going to use my fingers here, a mole of stuff is actually this number of atoms right here. And I like to write it like this because I think it's visual. If you take 4 moles and you times by a big number of atoms in a mole, You guys all with me here? You guys, I don't actually know nearly enough about what you've learned in junior high in math, but have you guys learned about how to like cancel things in math? Or if you have something on the top of a fraction and something on the bottom of the fraction, they can cancel?
Yeah.
Well, that's what we have right here. Here is a mole symbol on the top of a fraction. Here is a mole symbol on the bottom of a fraction. We can kind of cancel this symbol and this symbol right here, and that tells you how many atoms there are. So what we need to do is we need to take 4, and we have to times it by 6.02 times 10 to the 23.
Well, it's gonna be a big number.
It's going to be a big number. So let me walk you through a bit about how to use your calculators to calculate this, because I just told you the answer, but we need some calculator practice. So how many of you have like a fancy graphing type calculator like this one? Okay, let me start with you guys. Okay. So on button's down here in the corner. Here's what you would type in. You would type in 4. Then you would times by 6.02. Then you're going to times by 10. But then you got to do like a little exponent thing. And the button on these calculators that does exponents is this little up arrow kind of notch thing. And if you press that thing right there, some calculators will actually like lift your calculator up a little bit. Mine's an older one on here, it doesn't do that. But then we need to type in 23. 4 times 6.02 times 10. This means to the power of 23. And then we can now press enter. If you have a graphing calculator, it did not spit out the exact same answer that I had right here. But it's kind of similar. Do you see how there's a 2.408? And I have a 2.408. You got something different?
Mine says 55384.
Okay, everybody okay who's using a graphing calculator to get this number right here? Okay, your graphing calculator might use a different notation than I even just showed you. This little E symbol right here, E stands for times 10 to the power of. Because you see how this little 24 right here? It's that 24 right here. So if your calculator spits out an answer of 2.408E24, it actually means there's 24 times you'd actually have to move the decimal place over. Okay, who's using their phone? Okay, you can use your phone, but I'm going to highly recommend you start finding a calculator soon. But here's how you might use your phone. Okay. In my phone, you have to do it kind of backwards. The first thing you're going to want to do is find 10, and you got to try to find wherever the button is that goes to the power of 23. Sometimes it's written as like XY like that.
I got an XY.
You found that one there? So you got to go 10 X little Y 23. And hopefully it'll then say like 10E23. I don't know what it's going to say.
9.632E4.
Okay, I got to find this now.
Okay, so we got 2 sides. Yeah. There's a 10. This one right there? Yeah. 23.
It's going to be 1E23. Okay. And then what you're going to want to do is you're going to want to times by 6.02. You're also going to want to times by 4. And then you'll not have to say anything with that.
And you work backwards, really?
Work backwards. Yeah, you basically just got to do it in a backwards order. You got to do the power one first. Okay. Okay, any other questions on that in terms of calculator troubleshooting? Okay, let me show you a different analogy that's similar to this. Who has a job? How much do you make, Gabe, if you don't mind me saying?
13.
Okay, Gabe makes $13 an hour. When's the last time you worked, Gabe?
Friday.
How long did you work?
4 hours.
Okay, so let's say that Gabe made $13 an hour, and Gabe said he worked for 4 hours. Would it make sense then to take the $13 an hour and times it by 4? That's how much money he made total. But I'd like to show you how the units kind of cancel. Josh?
$52.
Pay attention. Ignore the tax part. Do you guys see how there's an hour symbol right down here on the bottom? And there's an hour symbol up here, but it's not on the bottom? Mathematically, these two things cancel. 4 times 13 is 52, but the only unit that's not been canceled is this money symbol right here. So then Gabe would have made $52.
Good job, Gabe.
Let me change this up though. Let's say that Gabe has a bill to pay and his bill happens to be $105. Here's my question. How long should Gabe work for to make $105?
8.5 hours.
26.
Well, that might make way more than that though.
No, he needs like 8.
Okay, so let me show you how you can calculate that without just guessing. Okay. Let's say that Gabe wants to make $105. And Gabe makes $13 an hour. Watch the first way I'm going to try this here.
This is cross multiplication.
A little bit, yeah. Let's say I times by $13 an hour. What's 105 times 13? Who's got a calculator nearby?
1,365.
Okay. Gabe, you will make $13 an hour. You want to make $105. Should you work for 1,365 hours to do that?
No.
This does not make sense. However,
Right.
I want to show, guys, can we focus a little bit more? I know it's Monday. Here is maybe a better way of writing it on paper. Gabe wants to make $105, but rather than saying he makes $13 an hour, what if I said that in 1 hour, Gabe makes $13? It's similar, but the difference now is that the $13, see how the dollar number is on the bottom of the fraction now? And this dollar number is on the top of the fraction, they cancel. Should I multiply these numbers? What happens if you have something on the bottom of a fraction? What does that mean you should do? You should divide, which maybe some of you already knew. So what's 105 divided by 13? Exactly, or 8.0. So therefore, Gabe needs to work for 8 hours in order to make this work. And here's one more thought. You know how this money symbol right here canceled with that money symbol right here? What's the only unit that I didn't cancel out? Hours. So that's why he needs to work for about 8 hours. My goal today is to show you guys how to do some chemistry calculations. You're either going to multiply or divide numbers. But I find that it's really easy, well, not really easy, but it's easier if you get a hang of like how to write it out so that you don't accidentally multiply when you should divide. Okay, you guys know how over the last, I don't know, I guess it was the last week or two, my focus has started shifting into writing sentences. Here is an example of a sentence. Methane plus oxygen makes carbon dioxide and water vapor. These numbers that we put right here, they were very important for law of conservation of mass. What they mean, Josh, don't apologize to me, apologize to the rest of the class.
Yeah, 6 dropped on there.
Okay, these numbers right here, they're very important for law of conservation of mass purposes, but they're also important for our recipe uses. You could consider that it means that 1 particle of methane and 2 particles of oxygen make 1 particle and 2 particles. But let's say we do a chemical reaction. Are we ever actually working with just 1 particle at a time? No. Usually we're working with lots of particles. Similarly, when you go buy eggs, do you ever buy 1 egg at a time? No, you buy a dozen eggs at a time. So same concept works here. What this means is that if you have 1 mole of methane, which is 6.02 times 10 to the 23, and you have 2 of oxygen, which is 2 times 6.02 times 10 to the 23, the same logic works. It's like upscaling your recipe. Rather than doing it 1 particle at a time, you're doing it 6 bajillion particles at a time. Make sense?
It's rich in particles.
Okay, here's a really key point then. Let's say we want to try to find a way to measure those particles. Is it logical for us to measure particles just by looking at them and counting that 6 bajillion number every single time? Unfortunately, no, it's not. But we do have a way of calculating a measurable value in the lab. We use a scale. What does a scale measure things in terms of unit-wise? Like what's the unit that a scale usually measures in? I'd say grams, maybe pounds, possibly kilograms, but mass is something we can measure. Here's the problem. Each atom has a different weight. Look at the periodic table. Hydrogen is number 1. It has 1 proton. Bromine is number 35. It has 35 protons. Are they going to weigh the exact same amount? No. There's a problem. If you like my analogies, maybe shift away from eggs. Let me use donuts. Let's say that when you went to Tim Hortons and you wanted to buy donuts, you know how sometimes you say, I want to buy a dozen donuts? What happens if rather than counting them out, because counting is going to be very inconvenient, what if you went there and said, I want to buy 5 kilograms worth of donuts? Now, at Tim Hortons, that doesn't really make sense. But I can think of other places where you buy things based on weight. Anybody ever been to the Marble Slab before? Where they make ice cream? They charge you based on how much weight you use, right? So if you eat a heavier ice cream, then it's going to cost you more. This is really loud. Thanks. Okay. We have a similar concept in chemistry that different donuts, or in our example, donuts are actually elements, they all weigh something different. And we have to account when we're trying to count these particles, or weigh these particles, well, how heavy are they? Hydrogens are light, bromines are heavy. So there is a number on our periodic table that I've kind of told you to ignore for the last little while, and it's a decimal number. Like for example, hydrogen is 1.01, or helium I believe is 4.00. You guys, can you find those numbers on a periodic table? You know where I'm referring to? Okay. Those are called a molar mass. Okay. And that is the average weight of that element. Okay. An individual particle of hydrogen either has 1 neutron or 2 neutrons or 3 neutrons. But we're not counting things one at a time anymore. We're now counting things 6 bajillion particles at a time. Does that make sense? And so when you have a billion different particles here, some of them could weigh 13, some could weigh 14, some could weigh 15, some could weigh 16. Does that make sense? Why can they weigh different amounts, by the way? Neutrons, yeah. Okay. Well, that number that I just referred to, the molar mass number, it's the average that you would expect to find in a mole. So if you were to go to the store, imagine there's a chemistry store, kind of like Tim Hortons, and you said, I want to buy 6 bajillion donuts, and I want those donuts to be hydrogens. Hydrogens weigh 1.01, they're very light. But if you went to the chemistry donut store and you wanted to buy chlorine donuts on average weigh 35.45. Now, if you bought just one donut, it can't weigh 35.45. It either has to weigh 35, or 36, or 37. Does that make sense? But you are buying a lot of them. So that's why we need an average instead. Does that make sense? So my goal on the next slide here is to help you figure out how heavy, how much mass you'd expect different compounds to weigh. Okay. So, for example, you guys are able to find how carbon is 12.01 on your periodic table? Okay, let's try an example here. I've written it out. NaOH. Anybody know what NaOH's name is, like what we call it? Perfect. Okay, so hypothetically, let's say you went down to the Tim Hortons chemistry store and you said, I want to buy 6.02 times 10 to the 23 donuts of sodium hydroxide. So you're buying 6 kajillion donuts.
Yeah.
That makes sense?
That's not even math.
Okay, but like, do you get the analogy at least?
Yeah.
Okay, so you're going to buy a lot of donuts. Each individual donut will weigh a different amount, but since you're buying a kajillion of them, we're going to find out how much on average they weigh. So sodium on average weighs 22.99. Can you guys find that number on your periodic table? Yeah. Oxygen on average weighs 16.00. And hydrogen on average weighs 1.01. What I've done is I've added this number plus this number plus this number. And it happened to equal 40 right on the dot. Does that make sense? So here's what that means. If you were to go to the store and you wanted to buy this many particles, 6 kabillion jillion particles, how much would they weigh? They would weigh 40 grams. Let's try another example. This one I had written out. Let's do a couple that aren't written out for you. Let's try to find the molar mass of what sodium sulfate is. So you know how like I used the donut example?
Yeah.
You just went down to the store and you asked for Boston cream donuts. And Boston cream donuts weigh this amount. Now you'd like to buy apple fritters. Do they weigh the exact same amount?
No.
No, they weigh something different. So we got to figure out how heavy is sodium sulfate going to be when you buy a whole bunch of them. So first question, what is sodium sulfate?
Oh, I got it.
Well, sodium is Na. SO4. Good. Sodium and sulfate is Na with SO4, but we haven't even done charges yet. So sodium's charge? Yeah, 1 plus. Sulfate's charge?
-2. Negative.
Good. So then, how do I fit this together?
You need 2 sodium.
2 sodiums. There we go. Okay, so before I can even do anything, there's the formula. So this is kind of like you go down to the chemistry donut store, and you're going to ask them for 6 bajillion donuts. Only this particular donut is actually not made up of just one thing. There's actually like a whole bunch of things shoved together in one super donut. This donut contains 2 sodium pieces, 1 sulfur piece, and 4 oxygen pieces. So I've got to use my periodic table then and figure out how heavy is this donut / compound. So let's try it. How heavy, according to your periodic table, is the average sodium atom? Anyone find that number? 22.99. Sodium is 22.99. Now, I want to make sure I'm really clear here. If you bought 1 donut of sodium, would it weigh 22.99? No. It would either weigh 22, or 23, or 24. But you're not buying 1, you're buying 6 kajillion of them. So therefore, the average donut's going to have some decimal numbers. Now, actually, not only are you buying 6 kajillion of them, but they come in groups of 2. So I'm going to take 22.99 and I'm going to times it by 2 because we're going to need 2 of them. I'll find that number in a second. Then we need sulfur. So the individual sulfur is going to be a whole number. However, because we're buying 6 gajillion sulfurs, how much does the average sulfur donut weigh? 32.07. How many of those do we need? Just 1, yeah. This particular massive conglomeration of donuts shoved together. Okay, the analogy works sometimes. It doesn't always work. But you need 1 of them. And then you also need some oxygen donuts. How heavy is the average oxygen donut? 16.00, yeah, like right on the dot. But how many do you need?
4.
Okay. So we now need to add all of this up. We need to take 22.99 and times by 2. We need to take 32.07 and times by 1. We need to take 16 and times by 4. So if you have a graphing calculator, I'll do it over here.
Are we recording this lesson?
I was.
You're not anymore.
Nope, we're 33 minutes in.
Cool.
Yeah.
Okay, sure.
So you want to watch it again?
42.05.
Okay, let me just do it on the calculator just to confirm though. So I'm going to go 22.99 times by 2. I'm going to add 32.07 times by 1. And I'm going to add 16.00 times by 4. Now, if you don't have a graphing calculator, don't try typing it in like this because it won't work. But hopefully you get 142.05. Anybody else get that number?
Yeah.
Okay, what does that mean? That means that if you bought 6 kajillion, like that big number, 6.02 times 10 to the 23, if you bought a crap load of donuts, how heavy would this particular box of donuts weigh? It would be 142.05 grams. That's how heavy those particular donuts weigh. Does that make sense? Okay, one of the things we might like to do then is convert between moles and grams. And one of the things I'd like to suggest then is when you find this number right here, we can write it as 40 grams per 1 mole, or we can write it as 1 mole per 40 grams. Very similar to an example I did earlier. Gabe made $13 per hour, or I could also say that in 1 hour, Gabe made $13. See how I'm flipping the thing upside down? It may be necessary to try to solve one of these next questions. So let me try an example. Let's say that you went and bought 6 grams of sodium hydroxide donuts. How many moles did you buy? So this is like going to Marble Slab. You go to Marble Slab and you say, I want 6 grams of ice cream. My question for you now is, okay, you bought 6 grams. How many moles did you buy? Did you buy 6 bajillion particles? Did you buy more than that? Did you buy less than that? Does that make sense? So, my first question is, how heavy is sodium hydroxide? Anybody remember from a previous slide how heavy sodium hydroxide was?
40 grams.
Ah, I heard it there. Sodium hydroxide was 40 grams per 1 mole. It was on a slide further back. I'm now going to write out 2 different ways of trying to solve this question. And I'm going to ask you guys to tell me which one's right. So just bear with me while I write 2 different ways, okay? Here's way number 1. I'm going to take 6 grams, and I'm going to multiply by 40 grams in 1 mole. Or, option 2, I'm going to take 6 grams, and I'm going to multiply, but I'm going to flip the fraction and say that there's 1 mole in every 40 grams. Which way makes more sense? The bottom one makes more sense. Here's a couple of reasons why. This gram symbol right here is on the top. Do you see how this gram symbol right here is also on the top? That doesn't cancel. But look at the one below it. See how the gram symbol right here is on the top of, technically there's not even a fraction, but see how it's not at least on the bottom of a fraction? You see how this grams right here is on the bottom of a fraction? That can cancel. This grams right here can cancel this one right here. Who has a calculator? What is 6 times 40? Is that 240?
Yep. Yeah.
If you require 40 grams to have a mole, but you only have 6 grams, do you even have a whole mole full? That was a mouthful. That was a mouthful of molefuls. No, you don't have enough. This first method doesn't even make sense. But if you have 6 grams, but it takes 40 grams to make a mole, well then, rather than multiply, what we're really doing is pretend you're extending this fraction the whole way over. Take 6 and divide by 40. Tired? There you go, 0.15. Do you even have a full mole?
How much is a mole again?
Well, a mole is 6.02 times 10. Like it's a lot of molecules, right? So you know how like a dozen is 12? We decided that a mole is like 6 kajillion billion molecules. Do we have 6 kajillion billion molecules?
Oh yeah.
Not if you have 0.15 of it. You have like
I thought you meant in this world.
well, in this world, sure. But in this example, do we have 6 kajillion billion molecules? No, you have 15% of it, I guess.
So we got like 25 million.
As opposed to 6. Okay. We're gonna try another example here. Let's say you go to the store and you say that you don't want a full mole. 6 bajillion billion molecules is too much for you. You want 0.250 of a mole. So you want almost a quarter of a mole. So imagine there's a gazillion particles right here. You don't actually want that many. You want almost a quarter of them. My question is, how heavy would you expect this to be? So I'm going to try writing this out 2 different ways. You tell me which one makes more sense. I'm going to take 0.240 moles, and I'm going to multiply by 40 grams in 1 mole. Or option 2, I'm going to take 0.240 moles, and I'm going to multiply by 1 mole over 40 grams. Which one of these 2 options is going to cause canceling of units properly? The top one's correct, yeah. Because what will happen is this mole's right here, and this mole's right here, they will mathematically cancel. So you need to take 40 and times by 0.240. And I got 9.6. Which I think kind of makes sense. If you need 40 grams for a mole, but you don't even want a full mole, you basically want a quarter of it. So what's a quarter of 40? Well, just under 10, I guess. This bottom method doesn't make sense. In a similar way, let me just try that money one more time just to make sure. Gabe wants to make $100, and he works for $13 per hour. This means Gabe would have to work for 1,300 hours to make $100?
8.5.
That doesn't make sense, does it? Or if you took $100 and you flipped it so that there was 1 hour for every $13. See how the money symbols would cancel? You're not actually multiplying. Extend the fraction and you're dividing. It's 10 divided by 13, which is $8, probably. 8 hours probably, right? Give or take. How am I doing so far? Does this make sense?
No.
This is a big leap because all of a sudden we're not just talking chemistry, we're talking math as well. Okay, why don't I do my last example, then we'll take a break. And when we come back, we'll find some more practice. Because I think I only have, what, one example left? Is this the last one? Okay, let me try one more example. And then we'll see how we did after this. So one more time, you're going to the chemistry Tim Hortons. And you would like to buy some donuts. But this time the donuts are not of sodium hydroxide. Now you're buying water donuts. Well, first we got to figure out, well, how heavy are water donuts? Does that make sense? So, what's water's formula?
H2O.
Okay. So H2O is made up of hydrogen. Well, how heavy is an individual hydrogen? Actually, no, that's the average hydrogen. I'm kind of being tricky here. An individual hydrogen either weighs 1 or 2 or 3, but how much does the average hydrogen weigh? 1.01, I believe, is the number in your data booklet. How many of them do you need, though? 2. Why 2? Well, there's a little 2 right there. Then you want to have some oxygens as well. Now, how much does an individual oxygen weigh? Well, it could weigh 14 or 15 or 16 or 17. But don't forget, we're not buying just one donut. This is like the Costco of Tim Hortons. You're buying 6 kajillion billion of them. So we don't care about an individual one. We care about what the average one weighs. And the average one weighs 16. So what is 1.01 doubled? And then also we need to add on 16 more. How heavy do water donuts weigh?
I feel like those would be really soggy.
Like I said, my analogy does not always work.
I don't think they'd sell very well.
I got 18.02. You guys able to calculate that?
Yeah.
Okay, so how do water donuts compare with sodium hydroxide donuts? They're way lighter.
Yeah.
Make sense? So that way you can probably buy more of them because they're not as heavy. Right? In the same way, if you go to like one of those make your own ice cream places, if you put like say whipped cream on, it's not as heavy. You can probably afford more. If you put on cherries are quite heavy for how much you get. Does that make sense?
Cherries.
I don't know. Give me examples. Okay, I'm going to try writing this out 2 different ways. Option A, take 2.5 moles and multiply by 18.02 grams per mole. Option 2, take 2.5 moles and multiply by 1 mole, but then divide by 18.02. Which one is going to cause a unit to cancel? Top or bottom?
The top.
Top. Because if you can see the way the top works, imagine that you extended the fraction all the way across. See how there's moles on the top right here and the bottom right here? Pardon me, they cancel. So all we have to do now is take 2.5 and times it by 18.02, and that's our answer. So someone help me out with the calculator who's got one nearby.
I got no. Yeah.
What'd you get?
45.05.
Yeah, you didn't put it down. You deleted it.
Anybody else get 4505? Anybody else try it yet? 4505? Okay, one last question before we finish this example. What unit is that 4505?
Grams.
Why? Why grams?
505.
Because see how right here there's a gram symbol right here, and I didn't cancel it? that must be the symbol left over. So it's 4505 grams. See how this symbol right here was not canceled, but the other ones were? Okay, let me try another example. Let's say that you went to the store, again, and you wanted to buy 11.20 grams of water molecules. How many moles would you expect? Well, we know how heavy water is. We just calculated it. So again, let me show you two ways of writing it out. You could take 11.20 grams, and you could multiply by 18.02 grams in 1 mole. Is that the way we should write this, though? Why not? Will something cancel from the top and the bottom of an equation? No, because where's my gram symbols? Well, one's up top here. You see how the other one's up top there as well? But this was not the right way to do it. So take that second fraction, but flip it upside down. Right, 11.20 grams, and then put 1 mole on top, and then on the bottom of the fraction, put 18.02 grams. Rather than multiply, what you're actually being asked to do is divide. So take 18.02. If you wanted to, you could times by 1, but that's kind of pointless. So what's 11.20 divided by 1802? Now, is there more decimal places after that?
Yeah.
Okay, so at some point you're going to have to round. We're going to talk a lot more about rounding in physics, because this is a hard enough topic on its own. But for right now, just round it to a couple of decimal places, and we'll actually talk about how far to round a little bit later in the year. One last question then. What unit goes next to this number? Yeah, moles. Why moles? Well, because look, here's the mole symbol that wasn't canceled. Okay, one last example, then we'll take a break. How many molecules would there be? Well, we just discovered that 1120 grams equals 0.62 moles. How many molecules or atoms are in a mole? 6 kabillion pajillion molecules. So if I wanted to figure out how many molecules there would be, I could write it like this. There are 6.02 times 10 to the 23. There are that many atoms. Atoms, molecules, same thing. There are that many atoms in 1 mole. You guys see how like that mole symbol right there can kind of cancel? So one last challenge for you. Grab your calculators. Let's try timesing those numbers together. I'll even do it over here. 0.62, then times by 6.02, then also times by 10, and then make sure you use the right button here. Use the little up arrow for 23. That's what I got. What does this mean? Well, it means 3.7324 times 10 to the 23 atoms. For some perspective, I'm going to write that number out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That's how many atoms there would be. Yeah, hopefully you guys can get the point though. Rather than counting things by individual atoms, that's ridiculous. Right? We're going to count them not by dozens, but by groups of 6 kabillion jillion, whatever that number happens to be. Okay, quick summary, and then we'll take a break here. This is where chemistry, we actually have to do something in chemistry. Up until now, everything up until this lesson has more or less been, can we write a sentence? Can we know our words? Can we know our letters? If this is something that you can do, I would recommend that you maybe go on in Chem 20. But if this is something where when we actually start applying the math sort of stuff to chemistry, if that went, it's not the big end of the deal for chemistry in grade 10, because this is our last topic. But this is kind of like the gateway topic to should you continue or not. Does that make sense? Because we can't just make chemistry all be about reading words and writing sentences. We actually have to do something with it math-wise. So, go take a break, and then when you come back, we'll talk about what we're doing for the next couple of days.